Hello students, after this lecture you will be able to explain the concept of electric field. We consider a Q charge at some point in space. Let us now consider another point charge Q0 which is placed at a distance r from this plus Q charge. Now the space surrounding this point charge Q, in which another charge Q0 experiences an electrostatic force of attraction or repulsion, is called the electric field produced by this point charge Q. This is actually the qualitative idea about the electric field, but we can also measure electric field or intensity of electric field quantitatively. In order to understand this, I consider that this plus Q charge is positive. This is known as source charge. This Q0 is now termed as test charge, which is always taken to be positive. Test charge is always taken to be positive. Now, according to Coulomb's law, the mutual force between these two charges can be written as F is equal to 1 by 4 pi epsilon 0 Q0 divided by r square into r cap, where I also consider a unit vector in the direction of vector r from capital Q to small q0. Now, the electric field or intensity of electric field due to this charge plus Q at any point r is the electric force per unit positive test charge placed at that point. Therefore, we can consider electric field E as force per unit positive test charge, which is equal to 1 by 4 pi epsilon 0 Q by r square r cap. This is also the electric field due to a point charge Q at any point can see that electric field is defined as force per unit positive charge. So its unit will be Newton per Coulomb. Later when we will be studying electric potential, we will show that electric field can also be represented as volt per meter. Okay? If we consider its dimension, Newton means kg meter per second square. So ml t to the power minus 2 divided by Coulomb. Coulomb is represented as ampere into time. So you can easily write it as ml t to the power minus 3 ampere to the power minus 1. When you bring this Q0 charge to this point, this will exert a force of repulsion on capital Q. As a result, this capital Q may move. It may move from this position to other position. Okay? And its electric field may get modified. So in order to avoid this, we always consider this plus Q0 charge to be very small. Thus the correct definition of electric field is limit Q0 tending to 0 F by Q0. It means that we are considering force per unit positive test charge where Q0 is very small. So now the electric field or intensity of electric field due to a charge Q at any point in space may be defined as the force per unit positive charge acting on a vanishingly small test charge located at that point. So this is how you can define electric field. If we consider a positive point charge Q, then the magnitude of the electric field produced by this point charge will be same on a sphere with the point charge located at the center of the sphere. That means it has a spherical symmetry, and the direction of this electric field will be radially outward. If we consider a negative point charge Q, again it has a spherical symmetry as before. But now the electric field points radially inward direction. So This is possible because here we have force of attraction on a unit positive test charge. Whereas if we consider this case, you have force of repulsion on a unit positive test charge, and that's why the difference. What is the physical significance of this electric field? So let us now discuss the significance of this electric field. The source charge, which may be a point charge or a system of charge, a system of charges, produces a definite electric field ER at every point R in the three-dimensional space. The value of this electric field may vary from point to point. Okay? Is that clear? The force on any test charge Q0 at point R may be calculated as F, which is also a function of R, that is equal to Q0 into ER. Right? Thus you may say that the electric field plays an intermediary role in the forces between two point charges. Right? Second important point is electric field E produced due to a point charge or a system of charges is the characteristic of the point charge. system of charges and is independent of the test charge used to determine the electric field. As you can see that electric field is a ratio of force and the test charge. Finally, you must keep in mind, even though mathematically electric field may exist up to infinity, in practice we consider electric field up to a certain region, up to a certain range, because after that electric field becomes very insignificant. So we may neglect the value of electric field after that certain point. Okay? Let us now discuss electric field due to a system of point charges. When we discussed the force produced on a point charge due to many other charges, for a system of charges, we mentioned that superposition principle is applied or superposition principle is valid. Electric field is also a force. That is why you can say that superposition principle still holds good. When we calculate the electric field due to a system of point charges, so we may consider a point P where I am going to calculate the electric field due to a system of point charges. You may have a system of 3 point charges. Let these charges be Q1, Q2, Q3. The electric field produced at point P due to charge Q1 may be represented by E1. I also consider this vector to be R1 and unit vector along in this direction as R1 cap. Similarly, you consider the electric field produced by Q2 at point P is say E2. So I consider this vector to be R2 and unit vector along this direction as R2 cap. So what to do? You have to add these two vectors applying law of parallelogram of vector addition. So this might be the resultant of these two. Let it be E dash. Now you also have a point charge Q3 which may produce electric field E3 at point P. This electric field E3 may be represented by this vector. Okay. As before, you consider the vector from Q3 to P as R3 and unit vector along this direction as R3 cap. If I now want to calculate the total electric field at point P due to all these charges, I now need to find out a resultant vector of this E dash and E3, and let us now consider this. Okay, so I am getting the resultant like this. Let the resultant be represented by E. So this is how you go on applying law of vector addition to find out the total field or resultant field at point P due to a system of charges. So we can write electric field at point P due to Q1 is U1 is equal to 1 by 4 pi epsilon 0 Q1 by R1 square into R1 cap. When I am calculating this electric field E1, the effect of Q2 and Q3 is neglected, as before I have discussed in the superposition theorem of electric forces. When we consider E2, this will be 1 by 4 pi epsilon 0 Q2 R2 square R2 cap. When I am calculating E2, I am neglecting the effect of Q1 and Q3. I can also calculate E3, that is the electric field produced by Q3 at point P, as 1 by 4 pi epsilon 0 Q3 by R3 square into R3 cap. If you have a system of n charges, so I may calculate all other electric fields like this, and finally electric field produced by nth charge Qn at point P is written as En arrow is equal to 1 by 4 pi epsilon 0 Qn by Rn square into Rn cap. So the total electric field produced at point E due to a system of n charges can be written as 1 by 4 pi epsilon 0 Q1 R1 square R1 cap plus 1 by 4 pi epsilon 0 Q2 by R2 square R2 cap plus 1 by 4 pi epsilon 0 Q3 by R3 square R3 cap. So you have n such electric field. So the nth term should be 1 by 4 pi epsilon 0 Qn by Rn square into Rn cap. So in compact notation I may write it as 1 by 4 pi epsilon 0 summation I is equal to 1 to n qi by ri square ri cap. So your running variable is from 1 to n. When you substitute I is equal to 1, you have q1 by r1 square into r1 cap. When I am substituting I is equal to 2, so next term will be plus q2 r2 square r2 cap. If we consider third term, then I is equal to 3, so I have third term as plus q3 by r3 square into r3 cap. So this is how you may consider many different terms. Okay, so this is the expression for electric field due to a system of point charges. So I believe that you have understood the concept of electric field. Okay, thank you.